Welcome to module 7 of the course Ultrafast Optics and Spectroscopy. In this module, we will study how to measure ultrafast pulse. An ultrafast pulse is represented both in time and frequency domains, which we have already seen in this course. In the time domain, we express electric field as a product of envelope function, field envelope, and carrier wave e to the power I phi t. And we have seen that this AT can be represented as square root of IT. On the other hand, in frequency domain, a pulse is represented as field envelope in the frequency domain and its spectral phase. And this field envelope is related to the spectrum which we record following this equation: A omega equals square root of S omega. Now, if we want to measure a pulse, we have to measure IT, temporal phase. So, this is intensity, this is temporal phase, and we have to measure spectrum or spectrum and spectral phase. So, these are the physical quantities we need to measure in order to represent a pulse. But if we look at the available devices for the measurement which we have, there are two different kinds. One is time sensitive detectors, including CCD camera, photodiodes, PMT, photomultiplier tube. On the other hand, in the frequency domain, we have grating based spectrometer. So, these are the two devices we have for the measurement. Now, unfortunately, available time sensitive detectors are way too slow to measure ultrafast pulse intensity profile and field oscillation as well. So, if we look at a pulse, let us say 10 femtosecond pulse or 100 femtosecond pulse, I have an envelope function. I am drawing here a transform limited pulse. So, if we think of the rise time and fall time of AT, this is of the order of, let us say, femtosecond. And also, if we look at carrier wave, the characteristic time of carrier wave is also femtosecond. This is we have already seen. But all the time sensitive detectors having response time of the order of nanosecond, 10 to the power minus 9 second, this one is 10 to the power minus 15 second. So, clearly they are too slow to measure either the intensity profile directly or the temporal phase in the time domain. So, if we try to measure anything faster with a slow detector, we end up with getting this. This is nothing but total energy content in the pulse. So, this integral what we measure with a slow detector. On the other hand, spectrometer can only measure spectrum. So, good thing about spectrometer it can directly measure S omega, which is present in the description of the frequency domain description of the pulse, but it does not give any spectral phase information. And we have seen that the phase information is very important. Spectrum gives how many frequency components we have, and phase gives how their phase are correlated. So, let us say I have two different waves having phase, relative phases like this, and another one like, so these two, if we look at, they are undergoing destructive interference. On the other hand, if they are like this, they are undergoing constructive interference, and we create the pulse. So, this is contributing to the pulse, and this is not contributing to the pulse. That is why having how many frequency components we have, knowing how many frequency components we have in the pulse is not enough information. We need to know how the phase or the relative phase of different color components. In spite of these problems, in this module we will try to understand how to measure a pulse with these devices. So, the first thing we will discuss is time domain measurement of ultra fast pulse. A time sensitive detector such as photodiode emits electrons in response to photon. So, if we direct a beam, laser beam to the photodiode, this will give me electrical response, and that electrical response can be plotted in an oscilloscope. Time sensitive detectors include photodiodes, photomultiplier tubes, but available time sensitive detectors have very slow rise and fall times of the order of nanosecond response time. So, the whole device, the detector including photodiode and the oscilloscope, they have nanosecond response time. On the other hand, if we think about the femtosecond pulse, it is rise time and fall time is of the order of femtosecond, and that is why if we direct a femtosecond laser beam to the photodiode to this configuration, then what will happen? Let us say that we are directing a beam of 100 microsecond pulse to the photodiode, then we will be able to immediately record the intensity profile of 100 microsecond, because response time of the detector is nanosecond, is much faster than the pulse duration. But if we take 100 nanosecond pulse, then oscilloscope, in the oscilloscope we will be able to see 100 nanosecond pulse as well. But if we take 100 femtosecond pulse and direct the beam to the photodiode, then what will be our observation? Our observation would be a nanosecond pulse, not a femtosecond pulse. And this is related to the total energy of the pulse, which is given by this integration minus infinity to plus infinity it dt. This is related to energy per pulse. Thus, detector output voltage is proportional to the ultrafast pulse energy. The slow response time of available time sensitive detectors does not permit us to make time domain intensity profile measurement of the ultrafast directly. So, then question is, how do we measure the profile? We measure the profile by a technique called autocorrelation with this device. Autocorrelation, which means you are asking the pulse to measure itself. That's called autocorrelation. A simple setup which can do autocorrelation measurement is Michelson interferometer. This is a configuration of Michelson interferometer where we have two mirrors and one beam splitter. So, input beam is split into two identical pulses. This input pulse is split into two identical pulses, 1 and 2, with the help of 50-50 beam splitter. And then we place this mirror on a motorized stage. That's why mirror can be taken backward or forward, and depending on where they are, depending on if this length is L and if this length is L minus delta L or L plus delta L, we introduce the delay between two pulses, and this delay is represented by tau. A 50-50 beam splitter will always create two identical pulses. So, if this is 50-50 beam splitter, then first 50% will be transmitted, 50% will be transmitted and 50% will be reflected. That's why a pulse I get two baby pulses. Then I have mirror here, and if the mirrors are placed at the equal distance, then they will again come back to this point after the reflection. They will come back to this 50-50 beam splitter at the same time, and again 50% of that baby beams will be, so this beam will be transmitted and this beam also will be reflected. So, this output beam is this 2. Now, if we step it back, then this is a longer path traveled by this arm or this pulse, and that is why after the beam splitter, this transmitted beam and the reflected beam will have a delay. This is called tau. Now, if we move the mirror backward by a distance L, let us say I have moved the mirror distance L with respect to the equal distance position. So, with respect to this point only, at this point this arm distance and this arm they are of equal distance. Now, with respect to this distance I have stepped back this mirror by a distance L. If we do that, then the delay can be represented as 2L by c, distance by c, velocity or speed, giving the time. This factor 2 is coming because light must travel and the extra distance to the mirror and come back from the mirror. So, it will go to the mirror and then come back. So, total distance travel is 2L. So, considering the velocity or speed of light as 3 into 10 to the power 8 meter per second, one can remember this, that 300 micron displacement yields a delay of 2 picosecond from this expression. So 300 micron displacement will give you 2 picosecond delay between two pulses coming out of the Michelson interferometer. So with this information, we can go back to the Michelson interferometer, and we see that in the Michelson interferometer we have now two pulses coming out of the interferometer. They have tau delay, and we have inserted now one SHG crystal, second harmonic generation crystal. Because these two beams are coming collinear, each beam will produce second harmonics, as well as there will be coherent generation of the second harmonic due to action, joint action of two beams as well. So in the intensity autocorrelation measurement, what we measure, we filter out 800 nanometer, that is the fundamental beam, and with the help of photomultiplier tube or a power meter, we just check total energy or total second harmonic generation energy. Because we are looking at second harmonic generation, it is called SHG intensity autocorrelation. So if we look at one more time the expressions which will be responsible to create second harmonic beam, here we have 50-50 beam splitter. The input beam is expressed as AT e to the power I omega naught t, that is ET, that is the input beam I have expressed. 50-50 beam splitter will split the intensity by into two equal intensity pulses. So we know that E is square root of I. And that's why the reflected beam and transmitted beam can be represented as 1 by square root 2 AT e to the power I omega naught t. And this one, this is transmitted, and reflected beam would be all again represented square root AT e to the power I omega naught t. Then due to mirror, I have a mirror here, I have mirror here. This beam will come back and again be transmitted through the 50-50 beam splitter. So that transmitted beam would be again 1 by square root of that beam that's the field. So one field is this one, and then again think about this beam. This will be reflected back and reflected by this 50-50 beam splitter. I get again 1 by square root 2 into that beam e to the power I omega naught t. So this is the total field coming out of the interferometer. which is, this is the pulse 1 E1 and this is E2, and total field is going to be E1 plus E2, which is coming out of the interferometer. Now, if we introduce a delay with respect to the other pulse, instead of t of the second pulse, we will write down E2 as, this is nothing but 1 by 2 at minus tau, at minus tau, that much delay I have introduced, multiplied by e to the power I omega naught t minus tau. So, this is the field which is delayed by tau time, and that is exactly what we have written. E out is the field coming out of the interferometer at this point, in the coming out of the Michelson interferometer. E out is represented by half, because square root, if we multiply 1 by square root 2 and 1 by square root of 2, we get half factor, then at into to the power I omega naught t. That is the first pulse, and the second pulse is delayed with respect to the first pulse, and that is half a t minus tau into e to the power I omega naught t minus tau. Then after this, what we have? We have an SHG crystal placed, and SHG crystal, SHG occurs because of the second order polarization, which means the term which will be responsible due to SHG, then SHG field is going to be nothing but E out square, and that is why we have to take the square of this whole term. If we take the square and if we do little bit of rearrangement of the terms, we get this. This is very easy to get, and then again reorganizing it, and finally if we have SHG field, then we can get intensity of the SHG, and that is square modulus of the SHG field, and SHG field expression we have got in the previous slide. So, we have to take square modulus of that, which is nothing but this multiplied by its complex conjugate, which is this one, and we get an expression for the intensity of the SHG field. Actual measurement, as I told previously, in the actual measurement we are not checking the intensity profile, but we are checking the total energy dumped to the detector, and that is given by V signal, that is related to total energy per pulse. When you use a power meter and check how much energy we have per pulse, that is exactly what we monitor. It is an integration of the intensity profile. So, in the end what we measure is proportional to this V signal, which is nothing but this expression. And in this expression, it is very easy to do this math. I mean, one can carefully look at the different terms, and then will be able to get this expression. Now, if we look at these first two terms, what does it mean? It means that they are the intensity of the SHG beam created by individual pulses. AT is the field envelope of the input beam. We have to first square it to get SHG field, and then I SHG, intensity of the SHG is going to be AT square modulus, which is nothing but AT to the power 4. That is why this is I SHG, SHG created by individual pulses. Each pulse, one of the pulses is not time delayed with respect to the other one is time delayed. So, each pulse is producing SHG and their intensities should be equal. Whether a pulse is time delayed or not, in the end their individual SHG signal should be the same. That is why we have this, they are equal, and in that case we can write down with a 2 factor and rest of the terms remains here. We will stop here and we will meet again for the same module.